it works, it'll be cool.
So what we'll do is we'll take one of the test tubes with the crab in it.
Yeah.
We'll put the test tube down here, which will keep the crab there. He'll come out and go, bang, hit the crab and smash the test tube.
Really? So the Mantis Shrimp it's a peacock Mantis Shrimp.
Yep.
Look at that joker. It's pretty awesome. Hey, don't they see more colors than any other animal?
Yeah, they've got incredible vision and their eyes are set up in parts of 3. So the top bits look in a different part from the middle, which is in a different part from the bottom.
Kind of like the fovea on our eyes is different than, okay.
Yeah. And we come, move little crab. Bang!
Triggered. Pulling out with that. Yeah, that's crazy. So let's back it up and watch again, and you'll notice that there's a cavitation bubble generated at the exact point of impact. Okay, first of all, a mantis shrimp isn't even a shrimp. It's actually a stomatopod. We call it a shrimp because it kind of looks like it, but we also call it a mantis because it's similar to a praying mantis with its forearms. They have similar hunting strategies. Dr. Seymour says that that punch is so fast that it can't be accomplished by muscle movement alone. There has to be something else going on. Which brings up Sheila Patek. Believe it or not, Dr. Patek has determined that the shape of this potato chip is the secret to the punch of the mantis shrimp. Seriously. This shape is called a hyperbolic paraboloid, and if you've ever taken calculus, you've seen it. It's basically a saddle shape, and they're super strong. This saddle is located on top of the smasher, and the stomatopod uses his muscles to compress it like a spring, and he holds it back with a latch mechanism. He then releases this potential energy, and it drives the club forward at a much higher velocity than would be possible with muscle alone. So the next time you eat one of these, remember, there's another animal eating with the same shape you are, only he's doing it at the bottom of the ocean, and he's got that shape integrated into the top of his arm. If you've ever played with a vice clamp before, you've seen this type of mechanism. You can slowly clamp down on the tool, which uses a cam over action to lock it in place. And if you have it set right and squeeze it hard, you store up mechanical strain energy. When you trip the latch, the energy is released and the arm flies forward real fast. But think about this. Mantis shrimp use their little clubber to break open shells that are really hard, right? So why does the shell break and the club doesn't? Let's watch another clip. This is Dr. Seymour feeding a crab to the stomatopod, except this time there's no test tube.
It's freaking the rock. Take the crab.
Oh! Did you get it?
Don't know.
Oh, I feel for that crab.
Watch again closer and see if you can see the saddle release the energy. Look at that. Good grief. Snapped it straight in half. We're talking about serious forces here. In engineering, we take two materials and we combine them together into composites to make them stronger. For example, plywood is made of many layers of wood with the fibers oriented in two different directions. Mantis shrimps, however, take this to the next level with an organic polymer called chitin. At the Wyss Institute for Biologically Inspired Engineering at Harvard, they determined that these fibers aren't rotated only in two principal directions like plywood, it's an entire helix, which gives the structure strength in many different directions. These strands are then bonded together in a mineralized matrix, which makes the whole thing an incredibly strong smasher. But it gets crazier than that. The team put a section of the smasher in a synchrotron so they could analyze the material makeup. A synchrotron. That's like a particle accelerator. This is crazy science. They bombarded it hundreds of times to understand the density and the local orientation of the crystals in the material. And guess what? They found that the crystals near the surface were oriented perpendicular to the impact site, and that orientation changed as we move away from the impact site. Basically, the material changes composition and strength at different locations on the inside. The impact surface is incredibly hard, but the internal structure transitions smoothly to allow the distribution of a huge impulse load throughout the rest of that structure so it can punch stuff all day long without breaking. So instead of a normal composite like plywood, which are identical layers stacked up and glued together, a mantis shrimp club is a variable composite, meaning you can vary the material makeup and the strength orientation wherever you need it. This is an incredibly smart way to design a system. In summary, I want you to love the mantis shrimp. I don't want you to love it just because of the mechanics of how it throws the punch. not because of the chemistry of the variable composition of the crystalline structure, the optics. It can see circularly polarized light. This is an incredible, incredible animal, and I want you to think about it every time you eat a chip like this. Can you do that for me?